Hello, everyone. Happy New Year. It's my pleasure to introduce Adam van Tuyl, who will give a talk on recent results on geometrically vertex decomposable ideals. Adam.
Okay, thank you, Irina, and thank you, Carl, for helping to set this up today and for inviting me. As I mentioned to Carl, I actually haven't been able to attend the Fellowship of the Ring before, so I guess, to force me to come, I had to come and give a talk. So thank you very much for the invitation. And I'm actually going to start my talk with an advertisement. As some of you may already know, and I saw some of my co-organizers on the call, there's in 2025, in the winter term, there's a thematic program on commutative algebra at the Fields Institute in Toronto. So it's going to run from January to June. There's going to be 3 main workshops. We're working on a summer program for summer workshop for graduate students. We're now taking applications for postdoc positions. They're 6-month positions at the Fields Institute. And we're also taking applications for long-term stays for like a month or 2 to stay in Toronto. So you can find all that stuff on the website for the Fields Institute, and we'll keep adding to that. Okay, so I just thought I should start with that. And I know many of you are at SLM Math this semester with another great thematic program going on, and I hope that those of you that are there are enjoying it. Okay, so as Irina mentioned, I'm going to be talking about geometrically vertex decomposable ideals. So kind of my goal really is kind of just to have a gentle introduction to what these ideals are, why you should be interested in them, and then talk about some new results with respect to these special classes of ideals. Okay, so I'm going to start with like a picture here. So I got some circles and squares and stuff. And you want to imagine the blue circle over here is the set of all simplicial complexes. And within the set of simplicial complexes, there are, of course, large classes of nice simplicial complexes. And the one, say this red box here, will correspond to things that are called vertex decomposable. Okay, so if you don't know this terminology, don't worry, I'm going to redefine everything in a couple of minutes or define everything in a couple of minutes. Okay, so this on the left-hand side is kind of a purely combinatorial objects. And on the right-hand side, we can think of the set of all ideals inside of the black box. And we have this one-to-one correspondence between the simplicial complexes and the square-free monomial ideals. And so what we would hope, okay, and it turns out to be the case, that special classes of simplicial complexes would correspond with special classes of square-free monomial ideals, okay? And so the part that kind of intersect the square-free monomial ideals, they're called vertex splittable, and I'll define that in a little bit. But the point of what I want to do in this talk is, what I want to do is ask, okay, is there actually a larger class of ideals? Okay, so that when we intersect it with the class of square-free monomial ideals, the overlap is precisely corresponds to the square-free monomial ideals that are that correspond to vertex decomposable simplicial complexes. Okay, so that's really the theme of my talk today, is how do we generalize the properties of the ideals, that the square-free monomial ideals that live here, associated to vertex decomposable simplicial complexes, to all ideals. Okay, so that's our goal, and that's, I hope you'll have at the end of this talk, you'll kind of understand how we could maybe generalize this family of ideals. Okay, so that's our goal. Okay, and again, I know there's some graduate students in the audience. We invited some of our own graduate students from the department to attend today. So I just wanted to quickly review some of the basic definitions and results here. So a simplicial complex is, we start with a set of vertices, okay? And a simplicial complex is just a subset of the power set of V, such that whenever you have an element, a set inside of your simplicial complex, and if G is a subset of that set, then G also belongs to the simplicial complex. And you also have normally the condition that each singleton set also belongs to your simplicial complex. Okay. The maximal elements of your simplicial complex are called facets. And if F1 and if F1 to Fs are the facets, right? You basically can describe the whole simplicial complex just using those facets. So we write F1 through Fs to denote the generating set, and that kind of makes sense, right? Because of the definition is once you know the maximal elements, all the subsets of those guys have to be in there. So we think, right, delta is generated by F1 through Fs. And we want to say that delta is pure if each of the facets have the same cardinality. Okay, so we'll be looking at simplicial complexes that are pure. Okay. Now, once you have a simplicial complex, right, we can make all sorts of new simplicial complexes from that information. Two that I need for today are the notion of the link and the deletion. So I'm just doing the definition with respect to a particular vertex, but there's a more general definition of link and deletion. So the link of a vertex is defined to be all the faces, elements of my simplicial complex, such that the union belongs to the union with X belongs to the simplicial complex, and F intersect X is empty. So this is called the link. This is the link of A in delta. And then the deletion is formed by taking all those faces that have non-empty intersection. Have an empty intersection with X. And it's sometimes called a deletion because another way to form that is to take each of your facets of your simplicial complex and then delete X from it, and then look at the simplicial complex generated by that set. Okay, so we have the notion of a link and a deletion, and then a particular type of vertex that we need is the idea of a shedding vertex. So a vertex is a shedding vertex if every facet of the deletion is a facet of your original simplicial complex. Okay, so some of these facets here, some of these subsets, you won't get any new subsets when you new maximal sets when you take this operation. Okay, and so this is called the deletion. Let me put that in. And that's the deletion of in delta. Okay. Now that we have that, we can actually define what it means to be vertex decomposable. Okay, so a simplicial complex is vertex decomposable if it's pure, and either it's the empty simplex, okay, or it's a simplex that has a single facet, or there exists a shedding vertex X such that the deletion and the link are also vertex decomposable. Okay, so if you haven't seen this before, the key thing to remember here is that the definition is recursive. Okay, so you have some of these base cases. If you're not in the base case, you try to break your simplicial complex apart into two things that are vertex decomposable. And when you're breaking it apart, you want to use a vertex that's one of these special vertices, which are the shedding vertices. Okay, so it's good to do an example. Okay, so let's say I'm a simplicial complex on 4 vertices. I've written my facets as AC, AD, and BD, and I'll draw the picture of that. So 4 vertices. I have C connected to A is connected to D, and D is connected to B. Okay. And let's just kind of do some computations here. So it's good to see some of these in action here. So the link of C is we're looking for all the subsets inside of my simplicial complex that when I add C, I get something in the simplicial complex, and it has the property that face intersects with C is empty. And if you stare at it for a bit, there's actually only one thing in this set, okay, or it only has one facet, the facet generated by A. And then the deletion, right, is defined by taking AC and you're subtracting C, you're taking AD and subtracting C, and you take BD, and you get not subtracting really, but set complement. There we go. And we this becomes A, this becomes AD, and this becomes BD. But remember, we're only interested in the maximal faces. So A is inside of here. So this is generated by AD and BD. Okay, and notice that every facet of this simplicial complex was a facet of my original simplicial complex. So C is a shedding vertex of my simplicial complex. And we step back and we're trying to decide, okay, is this simplicial complex vertex decomposable? Over here, this guy is vertex decomposable. We've bumped down into one of the base cases, but this simplicial complex is not in the base case. So you just have to say, can you do it again? Okay, and so we do it again. Okay, we let gamma be the simplicial complex of the deletion, and then we consider the vertex A. And it turns out A is the proper shedding vertex in this case. The link of A is D inside of gamma, and the deletion of A inside of gamma turns out to be the simplicial complex DB. Okay, and here we have a simplicial complex with one facet, and so it falls into our base case of being vertex decomposable. Okay? So one way I like to think about this is you have a simplicial complex, and you're looking for shedding vertices to split it into two parts, okay? And you want to keep splitting it until you get all leaves at the bottom, and all the leaves at the bottom are going to be vertex decomposable in the base case. Okay, so you want to kind of just think that you're just reiterating this process, okay? So you can see that, you know, if you want to prove something is vertex decomposable, probably induction comes in handy. You're basically hoping that either the link or the deletion would fall back into your family. And then you can say, well, I know that by induction, and then you can build it up. It could be that sometimes the case you have to do a whole series of breaking things apart before you can apply your induction. But this is the general procedure in which you show that something is vertex decomposable. Okay, so if we go back to my original picture here, right, I've kind of described all the stuff over here. So let's move back over to this part of the picture. Okay. So enter the Stanley-Reisner theory. I know this is the commutative algebra, algebraic geometry seminar, so many of you are already familiar with this. We have a one-to-one correspondence between all simplicial complexes and all square-free monomial ideals. And the correspondence is defined by, once you have your simplicial complex, you look at the square-free monomial ideal generated by all the square-free monomials, where you look at the corresponding variables and you look at that as a subset, and those things are not inside of my simplicial complex. Okay, so that's the definition, or the Stanley-Reisner ideal. So let's go to the next page, and let's go back to my my running example here. You just need to kind of look at this, and you're looking at all the square-free monomials that you can make on 4 variables, and then you're asking which of them don't show up in the corresponding subset does not show up inside of my simplicial complex. And it turns out that here you have AB, BC, CD, and then you get ABC, ABD, ACD, BCD, and ABCD. But in some ways, all of these other monomials here are overkill, right? Because the minimal generators of this ideal are just simply AB, BC, and CD. Okay, so there's my simplicial, my Stanley-Reisner ideal. Okay, so as I was saying, you know, you have this simplicial complexes, they get attached to square-free monomial ideals. You have vertex decomposable simplicial complexes, so they should be attached to some nice class of square-free monomial ideals. And this was actually done a couple of years ago by Murati and Koch and Ang. And they showed that your simplicial complex is vertex decomposable if and only if the Stanley-Reisner ideal is unmixed, so all associated primes have the same height, and Either you have that the ideal is generated by 1, the ideal is generated by a possibly empty subset of variables, or there exists a variable y and ideals I1 and I2 such that you can take your Stanley-Reisner ideal and you can write it as I1 intersect I2 plus the ideal y. Okay, and I1 and I2 are monomial ideals of vertex decomposable simplicial complexes. Okay, so you're basically kind of translating that whole splitting deconstruction property over to the monomial ideal side. So this is what Murati. Okay, so let me. My next comment here is, if you're now actually, and if you're actually jumping online and you're looking at the paper of Murati, Koch, and Yang, this is actually, you won't find this statement. I've actually translated, because they stated the original result using Alexander duality. So they used the Alexander dual of this ideal. Okay, and the reason that they wanted to use the Alexander dual is because before their work, it was well known that many of the properties of simplicial complexes are captured in the Alexander dual. Okay, and so for some of you, this is well known that if your simplicial complex is Cohen-Macaulay, we know that the Alexander dual, the ideal, sorry, let me say that right. The Alexander dual of the Stanley-Reisner ideal has a linear resolution. Okay. If your simplicial complex is shellable, okay, I won't define it here, but it's another special class of simplicial complexes. This gets captured in the Alexander dual again. The Alexander dual has linear quotients. Okay, and Murati, Koch, and Yang were then interested in, well, what is vertex decomposable? Hopefully that's captured inside of the Alexander dual as well. And they define what are called vertex splittable ideals. Okay, and so what I've actually done is I've taken this definition and then I just did the dual back just to show you what it corresponded in terms of the original Stanley-Reisner ideal. And the reason I wanted to do that is because it kind of matches up kind of what we're going to be doing next. Okay, so we have this now translation of this definition over to monomial ideals. It's good to do just a quick example. So here we have the Stanley-Reisner ideal of the same simplicial complex. Here's its primary decomposition, and we notice that it's unmixed. Okay, so that was the first condition that we needed. And we're going to look at the ideals I1 and I2. Then the variable C satisfies this, this property that the Alexander dual is the intersection of I1 and I2 plus the ideal C. It actually turns out to be, let me get my notes here and make sure I say that properly. It turns out to be the ideal BD intersect ABC. So you can check that this is actually that ideal. And we have I2 is contained inside of I1. Okay, this ideal here, this is my I1, it's generated by a subset of variables. So I've got down to my base case. This ideal, AB times C, is not in my base case, so I need to do it one more time, right? So I let J1 be B, J2 be the ideal 0, then the variable A satisfies the property that I2 is the intersection of the ideal generated by B and the ideal generated by 0 plus the ideal generated by A. Okay, and J2 is contained inside of J1. Okay, so what you have really is this decomposition of ideals. You're first using the variable C, then the variable A. And if you're familiar with the correspondence, moving things back and forth, really what's going on in the Murati, Koch, and Yang result is these ideals I1 and I2 are really corresponding to the link and the deletion. Okay, so I1 in this picture was the ideal of the link of delta of C. I2 was the ideal of the deletion of C. And then J1 was the ideal of the link of gamma of A. Okay, so it's just kind of you're porting over the translation. Okay, and so you're really these new ideals that you're creating correspond to links and deletion. Okay, so let me just scroll up here. Okay, is coming to our main theme, right? Which is how do we generalize this decomposition? What are the features of this definition that we want to use that we can extract and extend to all ideals? Okay, and the key insight here that you want to take away is generators of monomial ideals are automatically Grosvenor bases. Okay, so it suggests that if you want to generalize this, maybe you should be thinking everything in terms of Grosvenor bases and using Grosvenor bases to kind of split the ideal. Okay, and it turns out that that seems to be the correct way of generalizing the vertex decomposable decomposition. Okay, so getting to the main thing, main event here with the geometrically vertex decomposable ideals. I first want to give some background. So here, R is now going to be a polynomial ring in n variables, and we're going to just fix one of the variables, okay? And we'll just call it y. Okay? And for any polynomial in our polynomial ring, right, we can write it as a polynomial of y, right? We can write it as alpha d times y to the d plus alpha d minus 1 to the y d minus 1 up to alpha 1 times 1 plus alpha 0, right? Where alpha I is in my polynomial ring with the variable y removed. Okay. Now, once you fix a y, then you can talk about the initial y form, and it's going to be this top term right here. So the initial y form is going to be alpha d y d. Okay, so remember, alpha d is a polynomial, so it's not a monomial. It's actually a it could be a monomial, but it's in general it's going to be a polynomial. And now you can also take the ideal of initial y forms, right? So the ideal of the initial y forms is to take the initial y form of each thing inside of my ideal. Okay. And now that we have this, we also want to introduce special types of monomial orders. So a monomial order will be y compatible if first you take the initial y form, and then you take the initial term of that initial y form. So now we want to rip off the top monomial. That would be the same thing as if I just handed you the polynomial from the beginning and asked you to take the initial term of that polynomial. Okay, so it's kind of like you do a little detour, you go over and do the initial y form and then take the initial term. It doesn't matter. You could have just taken the initial term at the beginning and you would get the same thing. Okay, so it's a y compatible if you have this property for all your polynomials inside of R. Okay, and it's not hard to cook up examples of this. Probably the simplest example is if you were to take your initial y form to be, if you took your variable y to be x1 and you use the Lex order where x1 has the largest, is first in terms of your monomial order. Okay, so, and in fact, if I take in y equals x1 and I take any Lex order where I scramble up the rest of the variables, that would still be a y compatible monomial order. Before I go any further, was there any questions before I start using this about the definitions of the y compatible or the y compatible order? No? Okay. Okay, so now you have this monomial order and you take your ideal and you can just compute its Grosvenor basis. And so let's say that you've done that and you have G1 through GM is your Grosvenor basis with respect to this order. Okay. Now what you want to do is for each of the terms in your Grosvenor basis, you want to rewrite it, right? You want to rewrite it so it looks like Qi times y to the di plus ri, where this guy right here is the initial y form. Okay, so we have the initial y form of GI is equal to QI y to the DI. Okay, so we do this for each of my elements of my Grosvenor bases. And with that information, I'm going to make two new ideals. The first ideal, I'll call it just C, the ideal CYI, is you're going to rip off all the QIs that show up. Okay, so it's going to be the ideal generated by Q1, Q2, up to QL. Okay, so for each G gives you a QI and you use that ideal. And the ideal N, you're going to use some of the QIs. Okay, you're going to use particularly those QI where the exponent that shows up here, DI, is equal to 0. Okay, so this is the scenario where the elements of your Grosvenor bases don't have any term divisible by y. And this is, you use all the elements of your Grosvenor bases. Okay, you use all the QIs that show up. And the way that I've cooked it up, notice that these new ideals, the way these terms are defined, have no y in it, right? So they're ideals in one less variable than that we started with. Okay. Now, these ideals were actually first appeared in a paper of Knutson, Miller, and Yong in 2009. And they defined an ideal with a geometric vertex decomposition with respect to y if we have the property that the ideal of initial y forms can be written as CIY intersect with NYI plus the ideal generated by y. Okay, so what they proved is this ideal initial y form, it has this particular decomposition, and somehow using these new ideals here, we could say something about the original ideal that we started with. Okay, using this idea, Klein and Rajchgot in I forgot to put the date here. It was the paper finally appeared in 2021, but it was on the archive before that. They used this definition to define kind of the main object that I wanted to introduce today, which is geometrically vertex decomposable ideals. So an ideal will be GVD, or geometrically vertex decomposable, if it's unmixed. Okay, so all the associated primes have the same height. The ideal is generated by 1. It's generated by a possibly empty subset of variables. Or there's a variable y and a y-compatible monomial ordering such that you have this condition here, such that the ideal of initial y forms equals CIY intersect NYI plus the ideal generated by y. So you have a geometric vertex decomposition. And, okay, these ideals are in one less variable, and you have the condition that the contractions of these ideals to the polynomial with one less variable are GVD themselves. Okay, so this is the definition, and I was talking to Jenna earlier. She was telling me part of the motivation was they had this definition of geometric vertex decomposition, and they were using it to kind of recursively define a family of ideals. Okay. There's a couple of points I want to make about this definition. Okay, I guess first thing I'll just say is that's going to be the red box that I was hoping to introduce at the beginning of the talk. So that's what I'm trying to define, this big red box, and I'll justify why it's the right answer or can be viewed as the right answer in a second. What else did I want to say about this? Oh, the other thing is unfortunately, is that there's a lot of similarities between geometrically vertex decomposable and the phrase geometric vertex decomposition. Unfortunately, they both have, the same initials, GVD, and it can get you a little confusing when you first start it. But GVD here is we're referring to ideals where you have this decomposition and you can break it all the way down. Okay, and the geometric vertex decomposition is just breaking it at one particular step. Okay. Now, a couple other points that I want to highlight, especially for many of you, if this is the first time that you've seen it, is that there are some degenerate cases. Okay, and I'm just simply ignoring those cases just for this presentation. If you go look at Patricia and Jenna's paper, you can see some of this. Okay, the other thing, and this tripped me up, but it's partly my own biases because I deal with homogeneous ideals too much. The ideal I does not need to be homogeneous, right? So this is actually something that works for anything. You don't need the condition of being homogeneous. And the other thing that's kind of interesting is the monomial orders for the contractions may not be the induced orders. Okay, so let me just say something, say a little bit more about that fact there. Let's go back to the definition. You have, say that you've got to the step where you got to break it into the ideals C and N, and then you're trying to prove that these guys are GBD. You may have to start all over again and pick brand new monomial orders, Y-compatible monomial, or pick new variables with different Y-compatible orders to keep the process going. So it's not like you fix one monomial at the order at the beginning and you keep using it each time you move to the contraction. The tricky part here of this definition is you are allowed to change the monomial order as you move down. Okay. So those are kind of the things, especially for new people who are coming to this, that you might want to be aware of. Okay. And just kind of justify why this is in some ways the right definition is that when you take an ideal that's square free and you ask, okay, when is a square free monomial GBD? When does it satisfy it? It precisely satisfies it when I is the Stanley-Reisner ideal of a vertex decomposable simplicial complex. Okay, and in fact, if you were to go back to the definition or the result of Muradi, Koshin, and A, you can look at it, and it looks very similar to the way that I've defined GBD ideals, and I actually did that on purpose, so you can see the similarity there. And that's why I translated it from the Alexander duality definition to using it directly from the Stanley-Reisner ideal. And in fact, if you trace through all the definitions and everything, it turns out in the square free monomial case, the ideal C that you're decomposing it, one of the ideals that you're decomposing to, the ideal I, or sorry, let me say that again. The ideal C that you get when you're doing this decomposition, in the square free case, it corresponds to the link. Okay, and the ideal N corresponds to the ideal of the deletion. Okay. So if we go back to where I define these ideals, this guy here is supposed to be a generalization of the link, and this ideal here is supposed to be a generalization of the deletion. Okay, so that might help as we move forward here. Okay. This is a good spot to see if there's any questions. I can't see the chat, so are there any questions?
There is nothing in the chat.
Okay, thank you, Irina. Okay, so I should show that, you know, that there are actually some interesting things out there, and I'll just do a quick example of an ideal. Okay, so let's say that I take this weird polynomial. It's not homogeneous. F is 3x1 times x2 plus 4x3, x4, x5. And here's an interesting coefficient, log 2, 17 of x6. I'll use Lex order with x1, the largest element. And then the initial x1 form of f is going to be 3x2 times x1. And the initial term of f, right, because I'm using Lex order, is 3x2 x1, which of course is the same thing as doing this. And it's kind of a trivial example, but just wanted to show you how it worked. If we take the ideal generated by f, you know, it's a principal ideal, and so f is a Grosvenor basis. We take our f and we'll write it in this form. So it's equal to 3x2 times x1 plus my remainder. I'm really not that interested in the remainder. I'm interested in the coefficient of x1. So I strip off all the coefficients of things that show up of x1. That gives me my C ideal. There are no terms not involving x1. So my ideal n is 0. And the ideal of initial y forms f is equal to this. And it's quite easy to show that, or maybe everybody sees this. This is 3x2 intersect with 0 plus x1, which is the same thing as this guy right here. Right. So we have a geometric vertex decomposition. And both of these cases here are base cases. So these guys are GVD. So I equals F is GVD. Okay, so just a very simple example. And in fact, there's a much more general phenomenon going here, which is if I take any polynomial and I have the condition that each of the terms are square free and the support of each of those terms is disjoint, then the ideal generated by that form is GVD. Okay. Okay, well, those aren't maybe that interesting, right? I just wanted to show you a little bit about the ideals C and N, but you know, there are kind of very interesting classes of GVD ideals in the wild. Okay, in Patricia and Jenna's original paper on the topic, they proved that all Schubert determinantal, I can never spell determinantal, there we go, determinantal ideals are GVD. And more recently with Mike Cummings and Sergio da Silva and Jenna, when Mike was an undergraduate student at the time and Sergio was a postdoc at McMaster, we proved that all toric ideals of bipartite graphs are examples of GVD ideals, right? So this gives you kind of like a nice big class of ideals that you can make that are have this GVD property. Okay, and so you know, kind of keeping in the theme, it really is saying that you know these ideals should have in theory properties similar to vertex decomposable simplicial complexes. Okay. So in the last part of my talk, I kind of want to expand upon that, right? We started with vertex decomposable simplicial complexes. We've now built this large class of ideals, right, which we say should generalize vertex decomposable properties. So does it actually have, you know, what we want? Does it generalize things that we know about vertex decomposable simplicial complexes? Okay, and I want to summarize some of these results and talk about some new results here. So Patricia and Jenna actually proved in their original paper is that, you know, if I is GVD, then these ideals are radical. I is radical, and R mod I is Cohen-Macaulay. Okay, and this generalizes the well-known the result that if I'm going to green here. Try that again. If delta is vertex decomposable, then its Stanley-Reisner ring is Cohen-Macaulay, right? So we get this result as a special case of that result now. The other thing that Klein and Rajchgot showed was the following. They showed that if I is GVD, then I is Glichi. Okay, so that means that I is in the Gornstein liaison class of a complete intersection. Okay, I'm not an expert at liaison theory, but this is actually very nice. It really shows you kind of the usefulness of this new property because it gives you a tool to identify, maybe test whether a particular ideal is Glichi. And it actually generalizes a result of Uwe Nagel and Tim Romer, who proved the similar result originally for vertex decomposable simplicial complexes. Okay, so they proved that if delta is vertex decomposable, then the Stanley Reisner ideal of delta is Glichi. Okay, and when I was talking to Jenna earlier this week, she was kind of telling me that kind of what got her and Patricia kind of interested in defining GBDs was actually this result of Uwe and Tim about using simplicial complexes to build things that are Glichi, and so they were interested in, well, how do I expand that or how do they expand that result to build new Glichi ideals beyond the square free case. Okay, so you can start seeing already that GBD ideals, maybe you want to add them to be as part of your toolbox of interesting ideals. Okay, and then another thing that I did with Mike and Sergio was the following, and it's a nice result. It allows you to kind of build larger and larger GBD ideals. That if you take an ideal that's GBD in one polynomial ring, and you take an ideal J, which is GBD in another polynomial ring, then the sum of them is GBD in the tensor product. Okay, the tensor product of R and S. And this is great if you're looking at the toric ideals of graphs, and you want to show that your ideal is GBD. What this is really saying is you can worry about connected components. You only have to worry about the connected component part. And this actually generalizes a kind of a result in Provan and Billerud's original paper, where they were talking about vertex decomposable simplicial complexes, because they proved that if delta 1 and delta 2 are vertex decomposable, then the join of these two simplicial complexes is vertex decomposable. Okay, so this result here is kind of an algebraic analog of the result, this kind of combinatorial result. Okay, so already you're seeing here that GBD ideals allow you to kind of capture some of the same properties that you're used to with vertex decomposable simplicial complexes. So in the last couple minutes here, in the last part here, I want to talk about some more recent results that I have. And they're all kind of concerning invariants related to the Hilbert function and the Hilbert series. Okay, so just as a definition here, just a reminder, here we're moving back to homogeneous ideals. Okay, so if you have a homogeneous ideal, then the Hilbert function is simply the function that takes the value of I and maps it to the dimension of the ith piece of your ring. And then you can use this information to first define the Hilbert series. Okay, so the Hilbert series is defined to be this generating function. So this is the definition right here. Okay, where the coefficient of t to the I is the value of the Hilbert function when you plug in I. And then the Hilbert series theorem says that this generating function is equal to a rational function where you have some certain properties here. The D is equal to the dimension of this ring, and the numerator is called the H polynomial, and we have the property that the H polynomial is a polynomial with integer coefficients. So any homogeneous ideal allows you to build a Hilbert series, and so we get this object right here. And from this object, we can get other interesting invariants. One is the multiplicity. Okay, so the multiplicity of our ring, one way to define it is just the value you get when you plug 1 into your H polynomial. And the a-invariant, one way of defining it, is the degree of the H polynomial minus the degree. So it's actually the degree of this rational function. That's the multiplicity, the a-invariant, and one other invariant that we're interested in is the regularity. And I know most of you are familiar with the regularity from looking at the minimal free resolution, but we can do a little bit of a cheat here, because if we assume that our ring is Cohen-Macaulay, then the regularity of this of your quotient ring is simply the degree of your H polynomial. Okay, so if you haven't seen regularity before, you can just take this as your definition, because we're interested in GBD ideals, which are Cohen-Macaulay. Okay, so we get three kind of interesting invariants related to the Hilbert series. And in a recent preprint that I did with Nguyen and Jen Rajchgot, so Ty's a postdoc right now at McMaster. We posted it up on the archive in November, I think. And we proved that suppose that you have your ideal as a homogeneous GBD ideal, right? We need homogeneous to talk about all these invariants. And it has this decomposition. So you're going at the first level of your decomposition. Then if you're not in one of the degenerate cases, and that doesn't happen very often, falling into a degenerate case, you actually get some relationships between all of these invariants. So the regularity of this ring is the maximum of the regularity of the N ideal and the C ideal plus 1. The multiplicity is just the sum of the multiplicities. And similarly, the A invariant, okay, is the maximum of the A invariant of this ring plus 1 and the A invariant of this ring plus 1. Okay. And so because things are recursive, right, these ideals here, N and C, would be GBD, you can kind of reiterate the process. And then in some special cases, you can now kind of create closed form formulas for both either the regularity, the multiplicity, or the A invariant using this result. Okay, and this, let me give you the core idea of why this works, right? So the core idea is that, you know, the GBD property actually gives you a relation among the H polynomial. Okay, so it allows you to show that the H polynomial of the ring that you started with is equal to the H polynomial of the ideal NYI, right, plus T times the H polynomial of R modded out by CYI. Okay, so I didn't write plus twice, that's plus and a T. Okay, and once you have this, right, it's not too hard to show that the other results pop in. You have to be a little careful because, as I said, there's some degenerate cases you have to worry about. But in general, this is why all of these results hold. Okay, and you really need the GBD property to make this work because you want to keep track of the dimensions as you're doing things. Okay, so you can compare a Hilbert series. And let me just say, you know, that statement one, let me go back. This statement right here about the regularity, it actually a form of it already appeared in the literature for vertex decomposable simplicial complexes. So both Murati, Koshanang, and Ha and Woodrow proved that if delta is a vertex simplicial complex, but not necessarily pure. So I'm kind of sweeping some details under the rug here, but there's a notion of non-pure vertex decomposable simplicial complexes. And any vertex decomposable simplicial complex satisfies that the regularity is equal to the max of R mod the deletion and the regularity of R mod the ideal of the link plus 1. Okay, and remember what I was saying before, that the deletion is kind of the ideal N is kind of the analog of the deletion, and the ideal C is the analog of the link. And that's why our previous result is kind of a generalization of this. And in fact, we can recover this result when delta is pure. Okay. So that's kind of interesting. And I want to end off with some stuff that I think is kind of interesting about the Hilbert polynomial in this situation. So once you have the Hilbert function, okay, you can prove that eventually the Hilbert function behaves like a polynomial, and that's called the Hilbert polynomial, right? So there exists a polynomial, the Hilbert polynomial that agrees with my Hilbert function once I go significantly far. And you may have to go really, really far before you get some overlap, before those two things agree. But we can say that an ideal is Hilbertian if the Hilbert polynomial and the Hilbert function actually agree right from the beginning for all I greater than or equal to 0. And we'll say that an ideal is almost Hilbertian if it agrees except maybe at the first spot for all I greater or equal to 1. Okay. As you can imagine, not every ideal is going to have this property. Okay, so what's interesting, what Ty and Jen and I was actually able to prove is that if you have a homogeneous GBD ideal, then the ideal I is always almost Hilbertian. Okay, so GBD ideals agree with its Hilbert function at degree 1 and beyond. Okay, so that's true for any GBD ideal. And we can actually push it a little further in special cases. So we can improve it for the class of ideals of toric ideals of bipartite graphs. So we proved that when you're in this situation, then the ideal is actually Hilbertian. Okay, and you could have deduced this result from some results that were already in the literature, but I don't think anybody had actually explicitly stated this before, that toric ideals of bipartite graphs are Hilbertian, which I thought was quite a kind of a cute little result. Okay, and I've gone through the whole talk without a proof, and I do have a little bit of time, and I want to go back to vertex decomposable simplicial complexes. I'm stating the result for vertex decomposable simplicial complexes, but it actually holds for any GBD ideal. You got this result that the regularity actually can be no more than the dimension of the ring that you're working with. And if you're with a simplicial complex, that means that a vertex decomposable simplicial complex can have regularity at most the dimension of your simplicial complex plus 1. And I thought this was in the literature, and I looked, but I couldn't find it. And for your pleasure here, I'll actually give you the quick proof using all the pieces that we've done today. So how does the proof work? Well, we actually know when the Hilbert function and the Hilbert polynomial will agree. Okay, you can prove that it will agree if I is greater than or equal to 1 minus the depth plus the regularity. Okay, and this is just a general fact, and you can find it in the Geometry of Syzygies by David Eisenbud. And in our scenario, right, we have something that's vertex decomposable, so it has to be Cohen-Macaulay, so the depth is equal to the dimension. So we can replace this term right here with dimension. We also know that it's vertex decomposable. It implies that this ideal is GBD. So we know that this ideal is almost Hilbertian. So we know that this guy right here has to be less than or equal to 1, because we know for sure that the Hilbert functions agree starting at 1. It may have started earlier, but we know for sure it starts at 1. And then we just get this expression, and then we rearrange it, and we get the regularity is less than or equal to the dimension. Okay, so it's a nice little combinatorial commutative algebra result. But again, I didn't actually need vertex decomposable simplicial complex. A GBD ideal would have worked for this as well. So to kind of summarize here, okay, about what's next here. Oops. Okay. Well, we should identify other families of GBD ideals. Okay, maybe some of you are actually even thinking of your favorite families right now, and you want to check that they're GBD. Hopefully you go out and do that. It'd be nice to have more examples of this. My personal belief is, for the second point here, is that there are actually many other properties of vertex decomposable simplicial complexes that can be extended to the class of GBD ideals. So we can get a lot of inspiration from vertex decomposable simplicial complexes to get a much more general result. And as a final comment, okay, to encourage experimentation, I want to point out that there actually already is a Macaulay 2 package to do a lot of the stuff, and in fact more about what I talked about in today's talk. So the Macaulay 2 package is called Geometric Decomposability. It's already part of Macaulay 2, and it was written with Mike Cummings, who at the time was a undergraduate student at McMaster, and he's now doing a master's at McMaster as well. There you can find the archive, but we were just informed last week that it will be eventually appearing in JSAT. So I think that is about where I'll stop. So thank you very much for your attention.
Any questions, comments? Well, there are no questions in the chat.
Okay.
Let's thank Adam. This was a really nice talk. Thank you.
Okay, thank you, everyone.
Thank you.
Okay.
Thank you.
Enjoy the rest of your afternoon.